Chapter 7 takes us to the world of quantum algorithms. What are some of the important ones in this quantum algorithmic zoo?
This is where things get really interesting. Quantum algorithms are what set quantum computers apart from classical computers. They leverage superposition and entanglement to compute in ways classical computers simply can't. We'll start with some simple but powerful examples to illustrate the main ideas behind quantum algorithms.
Okay, I'm ready to be amazed. Let's see some of that quantum magic.
Let's start with the Deutsch-Jozsa algorithm. It's simple but elegant, demonstrating the power of quantum computation. Imagine a black box function, called an oracle, that takes a bit string as input and outputs a single bit. You need to figure out if this function is constant, meaning it always outputs the same value, or balanced, meaning it outputs 0 for half the inputs and 1 for the other half.
So it's a guessing game where we try to figure out the hidden logic of this black box.
You got it. Classically, you'd need to check the oracle with multiple inputs to figure it out. But the Deutsch-Jozsa algorithm uses superposition to query the oracle with all possible inputs at the same time. Just one query can determine if the function is constant or balanced. It's like asking the oracle all the questions at once and getting the answer in an instant.
It's like having a quantum cheat sheet for the guessing game. So it's not just faster. It's a totally different approach because of superposition.
Precisely. The Deutsch-Jozsa algorithm, as simple as it is, highlights a key idea behind many quantum algorithms, using superposition to explore multiple possibilities simultaneously.
Okay, I'm starting to see the quantum advantage here. What other quantum algorithms use this power of parallel exploration?
The Bernstein-Vazirani algorithm is another great example. It can find a hidden dot product string with just one query to the oracle, while a classical computer would need several. It's like looking for a needle in a haystack, but with quantum mechanics instantly narrowing down the search.
It feels like we're just scratching the surface of what quantum algorithms can do. Before we dive into more complex ones, you mentioned this concept of an oracle. Can you explain that a bit more? What exactly is an oracle and what does it do in quantum algorithms?
The oracle is a vital part of many quantum algorithms. It acts as a black box function that we can query to learn about the problem we're trying to solve. Think of it like a magic 8-ball that can answer specific questions about a function, but we don't know how it works on the inside.
So like a quantum expert giving us hints about the problem, but we don't know their secret knowledge.
Exactly. This oracle model is powerful for analyzing what quantum algorithms can do. It helps us focus on the algorithm's ability to efficiently get the information it needs by asking the oracle clever questions. It's about focusing on the strategy, not the specific moves.
I see. It's about the algorithm's ability to ask the right questions to get the answers it needs. Got any examples of how this oracle concept is used in a real algorithm?
Let's go back to the Deutsch-Jozsa algorithm. The oracle there represents the function itself. The quantum algorithm cleverly queries the oracle with a superposition of all possible inputs. Based on the oracle's answer, it figures out the nature of the function with a single query. It's like asking one carefully crafted question that unlocks the oracle's entire secret.
So the oracle is a quantum puzzle, and the algorithm is a master puzzle solver using superposition and entanglement to crack the code incredibly efficiently.
You got it. The oracle model helps us categorize and compare different quantum algorithms based on how many times they need to ask the oracle to solve a particular problem. We call this the algorithm's query complexity.
It's fascinating how this abstract concept is so important for quantum algorithms. Now, I'm eager to learn about more powerful quantum algorithms that can tackle real-world problems and maybe even beat classical algorithms by a long shot.
Get ready to be amazed. The next algorithm, Grover's algorithm, changes the game for searching unsorted data. It's a prime example of how quantum mechanics can provide a serious speed advantage over classical approaches.
I'm all ears. Let's hear how this quantum search engine works.
Grover's algorithm is incredible. It can search through an unsorted database much faster than classical search algorithms. Imagine searching for a name in a huge phone book. Classically, you might have to check every entry one by one, and that could take forever.
Especially now that we're used to instant search results on the internet, that sounds awful.
Absolutely. But Grover's algorithm gives us a quadratic speedup. That means if a classical algorithm takes n steps, Grover's algorithm can find the same thing in roughly the square root of n steps.
So it's not an exponential speed up like Deutsch-Jozsa, but still a big improvement, especially for huge databases.
It is, and it's really useful for problems where we don't know anything about how the data is organized. Things like searching for a document online, finding a specific combination to unlock a safe, or even cracking a password.
So how does it search so much faster? Is it using some kind of quantum trickery to cheat?
Not cheating, just clever use of quantum mechanics. Glover's algorithm uses superposition and quantum interference to make it more likely to measure the right entry and less likely to measure the wrong ones. It's like shining a quantum spotlight on the answer we're looking for.
So we're playing with probabilities in the quantum world. How does this amplification work?
It involves a combination of reflections and rotations in a high-dimensional space. The algorithm starts by putting all the database entries into a superposition. Then it repeatedly applies a sequence of quantum operations, each one bringing us closer to the right answer.
So it's a step-by-step process, like a quantum detective narrowing down the suspects.
Exactly. The number of steps needed is proportional to the square root of the database size, giving us that quadratic speedup. It's a beautiful example of how quantum mechanics can outperform classical approaches for certain problems.
Grover's algorithm is impressive. It makes you wonder, what other quantum algorithms are out there? Algorithms that could totally change entire fields.
Well, get ready for the next one. We're about to explore perhaps the most famous and potentially disruptive quantum algorithm, Shor's algorithm. This one can factor large numbers exponentially faster than any known classical algorithm.
Shor's algorithm. I've heard about its power and how it could threaten modern encryption. Can you finally tell us how this quantum codebreaker works?
Shor's algorithm is a game changer for cryptography. It uses quantum computation to efficiently factor large numbers, which is thought to be impossible for classical computers to do quickly. And here's why that's so important. A lot of modern cryptography, like the RSA algorithm, relies on the difficulty of factoring large numbers to keep things secure.
So Shor's algorithm doesn't directly attack the encryption, but goes after the math that makes the encryption strong.
That's right. It's like finding a secret weakness in the fortress of modern cryptography, a weakness only quantum computers can exploit.
I'm hooked. Tell me, how does this quantum code breaking actually work?
Shor's algorithm is a bit more complicated than the others we've talked about, but we can break it down. The first step is finding the period of a modular exponential function.
Uh-oh, modular exponential function.
Sounds complicated.
It's simpler than it sounds. Imagine repeatedly multiplying a number by itself and taking the remainder after dividing by another number. The key is that finding the period of this function is directly related to factoring the number.
So it's like finding a repeating pattern in a sequence of numbers, and that pattern helps us break the code.
Exactly. For classical computers, finding this period, especially for big numbers, can take a long time. But Shor's algorithm cleverly uses quantum mechanics to find the period quickly.
Okay, hit me with the quantum magic. How does it do that? It uses a combination of quantum superposition, the quantum Fourier transform, and some clever manipulation of quantum states to isolate the period of the function. It's a beautiful example of how quantum mechanics can provide an exponential speedup.
We're going deep down the quantum rabbit hole. But can we actually run Shor's algorithm on real quantum computers, or is it just a theoretical idea for now?
That's the million-dollar question. While Shor's algorithm has been demonstrated on small quantum computers, factoring large numbers like those used in RSA encryption would require much larger and more stable quantum computers than we have right now.
So it's a race against time. As quantum computers get better, the threat to modern encryption becomes more real.
Precisely. The potential of Shor's algorithm to break encryption has spurred a global effort to develop post-quantum cryptography, new encryption methods that are resistant to attacks from both classical and quantum computers. It's a fascinating and crucial area of research showing the huge impact quantum computing could have on our digital world.
It's exciting and a little scary at the same time. But it's a reminder that technology is a double-edged sword, and we need to be ready for the challenges that come with it. Before we wrap up quantum algorithms, there's one more thing I'm curious about: the quantum Fourier transform. You mentioned it when talking about Shor's algorithm. Can you tell me more about what it is and why it's important?
The quantum Fourier transform is essential in many quantum algorithms, including Shor's algorithm. It's the quantum version of the discrete Fourier transform, which is used in signal processing and other fields. Basically, it lets us break down a quantum state into its frequencies, just like a prism splits light into its colors.
So it's like taking a quantum signal and separating it into its basic parts.
Exactly. And what's amazing is that we can do the quantum Fourier transform efficiently on a quantum computer, making it a powerful tool for working with quantum information. In Shor's algorithm, we use it to find the period of the modular exponential function, which is the key to factoring the number.
So it's like a quantum lens that reveals hidden patterns in quantum states, patterns that are essential for solving certain problems.
That's a great analogy. The quantum Fourier transform is fundamental to quantum algorithm design. It allows us to do computations that classical computers simply can't do.
It's incredible how researchers and mathematicians have come up with these quantum algorithms. They've found ways to use the strangeness of quantum mechanics to do things we once thought were impossible.
It's a thrilling time to be working in quantum computing. As quantum computers keep getting better, we can expect even more groundbreaking discoveries and applications that will change our world in amazing ways. We've covered a lot of ground, haven't we? From classical bits to quantum algorithms, it's clear that computing is changing in a big way. But Chapter 8, Next Steps, reminds us this is just the beginning.
Right, it's like we've gotten a glimpse of something amazing, but the path ahead is still being built. What does the book say are the key challenges and opportunities in this next phase of quantum computing?
The book emphasizes that building practical, large-scale quantum computers is a huge challenge. It requires pushing the limits of physics, materials science, and computer science. Remember decoherence. That's a major obstacle for quantum computers.
Yeah, that tendency of qubits to lose their quantum properties because of noise, like building a house of cards in a windstorm. What are people doing to tackle this decoherence problem?
It's a multi-pronged approach. First, physically isolating qubits from their environment is crucial. Things like cryogenic cooling, where qubits are kept super cold, help reduce vibrations and shield them from stray electromagnetic fields. It's like creating a safe haven for the qubits to do their thing.
So we're making quantum refrigerators to keep those qubits calm and collected.
You could say that. But even with the best isolation, errors can still happen. That's where quantum error correction comes in. Remember those codes that use redundancy and entanglement to protect quantum information?
Yeah, like a quantum repair crew standing by to fix any damage to our qubits. But we talked about how error correction itself adds complexity to the system.
Definitely. Those quantum error correction kinds need extra qubits and quantum gates, which makes the whole system more complex. It's a trade-off, trying to protect the information while keeping the system manageable, a balancing act between resilience and efficiency.
It sounds like building a reliable quantum computer is a massive challenge, one that needs brilliant people from all sorts of fields.
It is. But the progress is amazing. Researchers are always working on new qubit technologies, better error correction codes, and smarter control techniques to push the boundaries of what's possible.
So there's a lot of hope and excitement on the hardware side. But what about software and algorithms? Are there limitations or challenges in developing quantum software that can really use the power of these quantum machines?
Absolutely. Creating efficient and useful quantum algorithms is key to unlocking the power of quantum computing. We have some impressive theoretical algorithms like Shor's algorithm for factoring and Grover's algorithm for searching, but designing new algorithms for real-world problems is tough.
It's like having a powerful tool, but we're still figuring out how to use it properly. What are some of the biggest obstacles in designing quantum algorithms?
One challenge is that quantum algorithms require a completely different way of thinking than classical algorithms. We have to use the unique features of quantum mechanics, like superposition and entanglement, to design algorithms that take advantage of those features. It's not just about translating classical algorithms to quantum, it's about a new way of thinking about problem solving.
So we need a new generation of quantum programmers, people who think in qubits and entanglement, who see the world through a quantum lens.
Exactly. And not just programmers, but a whole ecosystem of quantum software developers, algorithm designers, and experts from different fields who can connect quantum computing to real-world applications in medicine, material science, finance, and artificial intelligence.
It's an exciting time to be getting into quantum computing. It feels like a new era is starting, where the lines between different areas of science are blurring and new possibilities are popping up everywhere. But like any powerful technology, there are risks and ethical issues to think about.
The book acknowledges that, reminding us that we should always consider the broader impact of technological progress. As quantum computing becomes more advanced, we need to think carefully about how it will affect society.
What are some of the ethical challenges we need to be aware of?
One concern is bias in quantum algorithms. Just like classical algorithms, quantum algorithms can be biased based on the data they're trained on, which could lead to unfair or discriminatory outcomes.
So we need to make sure the data used to train these algorithms is diverse and representative, and that the algorithms themselves are fair and unbiased.
Exactly. Another concern is the potential impact on jobs. As quantum computers get more powerful, they might automate tasks currently done by humans, leading to job losses in some areas.
It reminds us that even though advancements are exciting, they can bring social and economic changes that need careful management.
Exactly. We have to think ahead about preparing the workforce for the quantum age, offering education and training so everyone can benefit from this revolution.
It's a call for responsible innovation, making sure that technological progress benefits everyone and doesn't worsen existing inequalities.
I couldn't agree more. As we embark on this exciting quantum journey, we need to be aware of both the opportunities and the challenges that come with it.
Well, this has been an incredible deep dive into the world of classical and quantum computing. From simple bits to mind-blowing qubits, we've seen how computation has evolved and the incredible potential of quantum computing to transform our world. But it's not just about the technology, it's about the ethical and societal implications too.
Absolutely. It's a journey that needs scientific and engineering skills, but also a strong sense of responsibility and a commitment to using these powerful technologies to make the world a better place.
So as we move into this quantum future, let's approach it with both excitement and caution, embracing the possibilities while being aware of the potential downsides. Thanks for joining us on this quantum adventure. We'll see you next time for another deep dive into a fascinating topic. Until then, stay curious.